Okay, good morning, everybody, and welcome to Papalim Physics Classroom. Okay, today we will be doing a review on one of the past year paper for 2023 for science physics. Okay, today we'll be using Holy Innocent High School paper. Okay, same as before, the video will consist of paper 2, the whole question from question 1 all the way to the last question. So it will be a long video. Okay, so if you need to check your answer at certain particular question, okay, just pause the video and you can just scroll to the particular area. Okay, so you don't need to watch the whole video. Okay, for those who don't have the paper, but you are interested in trying out the paper, I have left the paper in my Google Drive, and the link is at the comment bar at the description panel below. Okay, you can feel free to just go and click on the Google Drive and try out the paper. Okay, it's a good paper with some interesting question. Okay, so without delaying, okay, let's start the paper. Now, for this paper here, okay, I have listed down some of the interesting questions that students may want to take note. Okay, the questions here being interesting as in these are the questions that are like could be the answers are actually quite useful or quite interesting, or could be the questions, the way the question is phrased is actually one of the not one of the common variations. So the students may want to actually take note of these particular questions. Now, for question 1, okay, one of the common thing when you look at measurements are what are the precautions that the user can actually take. And one of the common precautions that we actually ask students to take note of are actually place your eye directly above the reading to read it perpendicularly, okay, to avoid parallax error. The other one that students may want to take note is that another method that we take off is to actually take multiple measurements at different locations, okay, whereby we actually make the measurement not just at a particular point, but actually maybe we can take the same measure. As example, for this case, we want to measure thickness of the assessment book. Okay, so instead of measuring the middle, the thickness and the middle, we can actually look at the measure thickness at the front, at the middle, and at the back portion of the spine of that assessment book. Then after what we do, when you got all the 3 or 4 measurements, so what we do, we'll take average to get a value of this. Okay, so by taking the measurements at different area and taking average, we are actually trying to reduce the possible errors that we actually be committed during the measurements. So these are the two possible, the two common, I would say, the two common precautions that user can actually take notes. Part 2, okay, the question asks for specific measuring instruments, and these are, as in, we will choose digital micrometer screw gauge, partly because, why? Because the precision of the instrument is better. Okay, you can actually measure up to 3 decimal place in mm. But here we are looking, as in, other than the fact that micrometer screw gauge is actually more accurate, but is it suitable? How do we know whether this instrument is suitable, or should we use a digital caliper? Okay, so whether this is suitable or not actually depends on what we need to measure. And in this case, we're actually looking at the thickness of 1.24. Okay, for digital micrometer screw gauge, the maximum reading we are looking at, the maximum range we are looking at for most of the digital micrometer screw gauge is actually a maximum of 25 mm, or what we call 2.5 cm. Okay, so for your micrometer screw gauge, okay, you can actually maximum of 2.5 cm. So between 1.24 is still within the boundary. So which means that this instrument is actually very, very suitable to measure this particular thickness of 1.24. Okay, so for range of different apparatus, for rulers, for digital calipers, for digital micrometer screw gauge, it's important that students need to know what are the possible maximum range the instruments can measure, and from then decide on which instruments is the most suitable one. The rest at the bottom will be quite standard where I look at the mass of the from weight to calculate mass. So in the sense that the standard way we look at weight is actually mg. Okay, so when I give you the weight, okay, I should give weight, I should be able to find the mass. Okay, partly because we know that the gravitational field strength is actually 10 Newton per kg. So the math, I will not dwell too much on this. Density, same thing, basic formula, mass over volume. Okay, so this is the basic formula for density. Now, for density, students may want to take note is that the way the question is phrased. Sometimes the question will actually ask you calculate the density of a liquid. Okay, so if it's calculate density of a liquid, point to take note or possible variation is actually they will give you volume. Okay, volume of maybe it's an empty container. Then after that, I will give you another one. We give you the volume of the water. This should be XXX amount Okay, volume. For this particular type of question, students, you will need to take note is that the mass, okay, the mass of the liquid. If I want the density of the liquid, I need the volume of liquid, I need to know the mass of the liquid. And in this case, the mass of the liquid, based on the picture here, you actually know that the mass of the liquid here, the mass of the liquid actually consists of the empty container or the empty measuring cylinder. So once you have the mass of the water and the cylinder, remember, must subtract the volume, must subtract the mass of the empty cylinder because I only want the mass of the water added only. So this is one variations that that density question can come out lah. Okay, so in this case, for this particular question, I will not dwell too much. Now for question 2, question 2 is about moment question. Is about objects, several objects being hung together on a few rods. Now, one of the common question, the question asked for part B is the tension of the string. Tension in the string. Now, tension in the string here we're looking at is actually here. This is string A. Now, string A is actually supporting these 4 different objects. So all these 4 objects are actually pulling down on string A. And of course, the assumption here is that the rod and the weight of the string is actually negligible. So in this case, we are looking at 4 items. So pulling down on string A. So the most obvious one is actually I will need to know the weight of the 4 items acting on string A. And from there, I can just add them up together. Now, but what happened here is that we actually do not know the last weight of the last object on the left. Okay, but we do know that the moments are actually balanced. Based on the question is that the moments of the beam are actually balanced. Okay, these beam are balanced. Okay, so which means that the clockwise moment and the anti-clockwise moment for the rod 1 is actually balanced. So which means that if the perpendicular distance of both items is actually the same, 5 cm, 5 cm away from the pivots, okay, so the middle point will be the pivots. Okay, so if the perpendicular distance is the same and they have the same moments because they are balanced. Okay, so moment, remember, it consists of force times distance. Okay, so if both of them got the same moment because they are balanced, if both of them got the same perpendicular distance, okay, which is 5 cm, and if these two are the same, it would allow us to actually deduce the fact that the force on the rod 1 will actually be the same. And from there, I will be able to know that actually rod 1, the weight of the circle or the weight of the object on the left is actually 8 Newton. And once I got 8 Newton, I will just add up all the forces acting on the rod or on string A, and I will get a total of 26 Newton. Now, for part B, okay, part B here, we look at the calculate the distance x. So where is x now? Okay, so where is x? Let's take a look. Where is x? X. Oh yeah, x is here. Now, same thing as before, based on the question is that the rod is balanced. So which means that the rod 2 is actually performing this. Okay, your anti-clockwise, you got a clockwise moment. So your rod 2, where we are looking at, so this is your rod 2. Okay, so between the moment will be the same. And for the moment to be the same, it will means that I need to factor in the perpendicular distance for the 2 objects. Okay, and actually the weight of the 2 objects here. Okay, so if it's clockwise, anti-clockwise, equal to clockwise. Okay, so if I take in all the forces, which is 6 and 4 Newton, and I factor in their perpendicular distance, which is 7 cm for perpendicular distance. Okay, so this will be a 7 cm for perpendicular distance of the 4 Newton on the left, and x will be a perpendicular distance on the right, okay, with respect to 6 Newton. So from here, I will know that actually since that the moments are the same, okay, I'll factor in all the moment calculation, 7 times 4, which is the left-hand side, and clockwise moment, which is 6 times x. Okay, so x is actually the perpendicular distance. And from there, I'll be able to work out the perpendicular distance, okay, of the object, okay, for the second figure. Okay, so just take note of this. Okay, so when we look at your perpendicular distance, it's most important to know where moments. Sorry, when we look at your moments, it's most important actually to look at your perpendicular distance, your force, and even your clockwise and clockwise moment. And from there, I'll be able to deduce more informations. Okay, so just take note of the math. Part A, definition of principle of moment. Okay, so the common mistake for part A is actually when students mistook it for the definition of moments. Okay, mistook it to define moments. Okay, so for principle of moments, okay, it has a few keywords that we're looking at. So we are looking, if we define principle of moment, you have to tell me that it is actually due to equilibrium. And you have to tell me the total anti-clockwise moment equal anti-clockwise moment. And the last one that you need to tell me is actually all these took place about the same periods. Okay, so in fact, actually most of these textbook or all the textbook actually will actually properly define principle of moment for you. Okay, and all the definition will actually consist of these 3 points. So for principle of moments, it's important, okay, to know what you are looking at and what keywords are you using. Okay, principle of moments and moments are. Now for question three here, we will see that we are dealing with a hydraulic press. Hydraulic press usually work on the principle that the pressure is actually transmitted equally, okay, throughout the liquid. So which means the concept they are looking at, it could be a several piston, so whereby you have your pressure 1 equal to your pressure 2. Where transmitted equally implies that the pressure actually remains the same. Okay, that's the basic principle of your hydraulic press. So here we have a small piston. On the other side, we actually have a large piston. Okay, so one of the most obvious things is that despite the different area, different in force, okay, the concept of hydraulic whereby your P1, okay, the P small, the pressure in the small, actually is actually being transmitted to the other end, okay, so the pressure experienced by the big piston, actually they are the same. Partly because why? Hydraulic press, remember, we are looking at oil, fluid basically. It need not be oil, it can be water also. Okay, but one of the important thing is it must not have air inside, because air, one of the characteristics of air is that air is compressible. So whenever if I exert a force or exert a pressure on air, because air is compressible, and what does it mean? That it means that the pressure will not be transmitted equally throughout the particular piston itself. So that's why when you look at hydraulic press, it is very important that you do not have any air bubble, or you don't have any air bubble inside the fluid here. Okay, so inside the hydraulic press, we have to make sure that the liquid actually consists of 0 or negligible bubbles. Because if I have bubbles inside, so whenever I exert the force at the one end, okay, the pressure will be transmitted, but some of the pressure is actually being lost because it is compressed the air bubble inside the particular fluid itself. The other common thing that we have is when we talk about fluid for hydraulic press, is oil versus water. Okay, so one of the common questions that you see is how come for fluid? Yes, fluid, I can choose actually any liquid that I wish. But you find that most of the time we actually avoid using water as the liquid, as the medium inside the piston. Partly also because water, it's not that water is compressible, no, it's actually all incompressible because they are liquids. But what differ oil and water is that water we don't like to use is because water actually will cause corrosion. So whenever you have water inside the piston, although it's a fluid, it does transmit pressure equally to both sides or to all the sides. But because water is corrosive, so if I were to use water inside the piston, and which usually piston is made of metal, so when I use water and metal, there are some tendency that the piston actually will start to rust after a few months, and because of that rusting, I will need to actually change the piston itself. Okay, so these are some of the common characteristics of why we actually uses hydraulic press. Now, for calculation, like I mentioned before, by the pressure in the big piston and pressure in the small piston, they are actually the same. So when we look at hydraulic press, the first thing that we always do, actually, we look at the pressure at one end. So in this case, we start with the small piston here, the force exerted by the small piston and the area of the small piston. And given the question, the force exerted on a small piston is actually 300 Newton. And actually the pressure, the area that we are involved in the small piston here is actually 0.05 meters square, which is given in the picture actually. Okay, so these are the two information that is given. And with these two information, we are actually able to calculate the pressure, or we are able to calculate the pressure in the small pistons. And true enough, once you are able to identify the pressure at the small piston, we can actually relate it to the big piston, because the big piston, okay, it will be the pressure will be the same as the pressure in the small piston will be the same as the big piston. Okay, and from there you'll be able to find the force that will be translated to the big piston. Okay, remember for hydraulic press, the piston is actually the pressure is actually the same. Okay, for big pistons, and sorry, for the small piston is actually the same as the pressure at the big pistons. Okay, so that's why we are looking at the same pressure here, 6,000 Newton per meter square, or what we call 6,000 Pascal. Okay, so just take note of this approach. Okay, usually for hydraulic press, the math usually, I would say most of the time, you always roughly revolve around this formula here. So it's very important that students actually know how to apply the math. And one of the common things that we look at is, you must remember, is that for the force that you're looking at, the unit for the force, it has to be in Newton. So in any time, if you know that whether it's in kilonewtons or if it's in kg or this thing, remember to change whatever unit they give you to the correct unit. And in this case, the correct unit for force is the SI unit for force, which is Newton. Now, step one modifications, okay, for hydraulic press, okay, that will require a smaller force to be exerted on the small piston, okay, to achieve a larger force in the big piston. Now, regardless of the force exerted, okay, so the concept of hydraulic press still remains the same, whereby the pressure at the big piston must be equal to the pressure at the small piston. So with this in mind, you'll find that the force of the small piston and the area of the small pistons, okay, the ratio of them actually is the same. Okay, the ratio of force and area is actually the same. So in this case here is if I want the force to be the small, if I want to exert a smaller force here, okay, to achieve the same force, okay, or with a bigger force now. So what should we actually do here? Now, so the most obvious one is, in this case here, if I want to maintain the same force, okay, I would actually need to maintain the same area. Why? Because I want to keep the pressure on the big piston to be the same. And for me to keep the big piston to be the same, or for me to keep the pressure of the big piston same and the pressure of the small piston to be the same, okay, if I use a smaller force now at a smaller piston, I will definitely need to actually reduce the area on my smaller pistons. It's possible that for me to achieve the same ratio, for example, maybe it was 300 Newton just now, for example, okay, random number. So if it's 1 Newton, if it's 4 Newton just now, okay, my area will be 4 meters square. So if I want to reduce the force now to 2 Newton, okay, if I want to maintain the same ratio, okay, so I actually have to reduce the area to 2 meters square. Okay, so if I reduce the force, I need to reduce the area also by the same magnitude. So if I reduce it by half for the force, I would need to reduce the area by half also. Objective is to maintain the ratio to be the same. Remember, the ratio of F and area, force and area, actually will give rise to pressure. Okay, so things to take note for this particular question here. Okay, the way you change your area, okay, the objective is actually to maintain the pressure to be the same. Okay, the pressure for hydraulic, the pressure at both sides always remain the same here. Now, for question 4, I will not dwell too much because question 4 is actually is one of the O-level paper for thermal processes, okay, where we deal with conduction and convection. All right, so I would say that for students who have done your 10 series question, you actually find these questions to be familiar. So I will advise you to actually go and look up for the answer in your 10 series and actually take a look at the question. It's actually quite a good question where it covers convections and even conduction. Now for question 5 here we deal with the transmission of sound. Like I mentioned in the previous paper, when we talk about sound, one of the common questions that actually keep appearing is actually the transmission of sound. How sound is actually transmitted from one end to the other end. And this question, true enough, is that the answering technique is always the same. Yet we actually involve the use of like the students telling the marker is that the transmission of sound actually it actually consists of the displacement, the air particles, which is the main medium. And what does the air particle do? Actually, it actually have vibrate in this particular sequence. And what I always tell students that we need to actually to illustrate the sequence using the definition of longitudinal wave, because the definition of longitudinal wave actually give us a very clear explanation or definitions of how the air particles are being displaced. And in addition to this is when this movement, what does it do? It causes a series of refraction and compression, okay? And this series of refraction and compression is what gives rise to the sound. And this is how sound is being transmitted from one end to the other end, okay, by the arrangements of the particles. And what type of arrangement? A series of refraction and compression. For answer on how sound is transmitted, it actually involves two particular things, whereby student, you need to tell the marker that actually the definition of longitudinal wave and create a series of refraction and compression. And this allows sound to be actually moved, okay, from one end to the other end. Now, for the transmission of sound, for the part B, calculation of the sound interval, Now here you have to take note. Based on the question here is that the person, the woman in the middle is the one that who fired the pistol. Yeah, and the guy is standing behind it. So if you look at the transmission of sound in this case, when the woman press the pistol, okay, sound is actually being transmitted. In this case, there are actually two movement of sound. So for example, the moment sound is transmitted, one of the most obvious one is that there will be a sound wave transmitted to the right. Okay, it hit the building, and this particular wave will actually reflect back to the woman, and it will continue on to the man. And this is how the man actually hear the reflected sound. But for the man itself, this is not the only sound he hear. Okay, before he hear this particular sound, okay, the purple color one, he actually hear another sound first. Why? Because when the woman fire a shot from a piston, okay, the sound that's transmitted is not just to the right. Instead, there's also sound wave transmitted to the left, okay, which is illustrated by the green color line. So at the same time, while there's movement, there's sound movement, okay, to the right, okay, the sound is also transmitted to the left also. So all these two sounds actually move left and right, okay, concurrently. So the green color one in this case, you move to the man here. So in fact, if you look at the distance covered by the the sound wave, okay, the purple line and the green color line, you'll find that the green color line cover a lesser distance, which means that the man will actually hear the green color sound first, and then he will hear the purple color one. Okay, so that's why if you are the man standing behind the woman, and when the woman fire the shot from the piston, the man will actually hear two sound. In between, there's an interval, so he will hear the first green one, pause for a while, then he will hear the purple one another time, the second time. Okay, so two sound at a certain interval because of the distance covered that is different. Okay, so take notes. Okay, so what's the sound interval? Okay, the most obvious one is to calculate individually. So the first one will be the green color one. So this is the sound of the first one. Okay, the green color, which is traveling to the left, the green color one. Okay, so green color one, the green color only travel distance of 200 meter, and I know the speed of sound is 300 meter per second. So if I have distance, I have speed, I will definitely be able to find time for the green color one. So that's why I know it's 606. Yeah, correct. So second one for sound number 2. Okay, sound number 2 here refer to the one that's on the right. So the purple color one, so the purple color one. Okay, so for the purple color one, he actually travel 350 meter. Then after that, he travel another 350 meter first to reach the woman again. Then he travel another 200 meter before he reaches the man. So in fact, for the second sound, he actually travel a longer distance. Okay, so this is where the 900 come from. So it come from your 350 plus 350. Now, after the 352 times 350, I reaches the woman. I will travel another 200 meter to reach the man. In fact, for the guy here, he will actually travel, okay, the distance travel will be 350, 350, followed by 200. So a total of 900 meter. And if I know the speed and I know the distance, I will be able to identify the time taken for the second sound. And time interval, just take the difference between these two, and you will get the sound time interval. For this particular question, personally, I like this approach because this is the easiest, the most straightforward. Okay, whereby I look at for sound 1 first, then I look at sound 2. But I have to admit that this particular method is actually not the fastest, but it's definitely to me, it's the clearest. So some students, if you go at your math, you'll be able to find the interval in just one step working. Okay, by all means, go ahead and take a look. As long as your concepts are clear, okay, apply any math, okay, as long as it's logical and sensible. Question 6. Okay, question 6, we have a converging lens. Okay, converging lens, remember, in this question here, they actually give you the outcome first. They actually give you that the image form is actually virtual, upright, and double. The moment you see virtual, you will know that the object distance is definitely smaller than the focal length. Okay, so for me to be virtual, based on the ray diagram, okay, you'll find that the virtual and upright, yeah, and I have an image, okay, which means that this will be your ray diagram number 6. Okay, so whereby the answer for my object distance, it has to be smaller than the focal length. To draw ray diagram, remember, there are only 3 rays that we can draw. Okay, the first ray, which will cut through the optical center and go straight through without bending. This is ray number 1. Ray number 2 will be parallel ray to the principal axis, and you will hit the lens, and from there, it actually will it will actually cut the other side. It will cut the focal point on the other side of the lens. That will be your ray number 2. Ray number 3 will require you to cut the focal point first. But of course, in this case, I don't even know where's the focal point, so I will not be able to draw ray number 3. Ray number 2 in this case is like halfway there because it's stuck halfway. Why? Because primarily I don't know where is the focal point. So at this moment, this is where I stop there. But this doesn't mean this I can't continue. This doesn't mean I can't continue. What happened here is that based on the clue that's given, is double. The size is double. And for size to be double, I actually know that the image will definitely form along this line. So this is dotted line. I stand back, it will be dotted. It will form along this line. And the size, the image will be along this line and the size has to be double. So what I do now is I should actually go and measure the height of this object. And I actually double it. For in this case, will be here. Okay, so this will be the image. Remember, virtual, it means the light ray, the image will actually be dotted line here. Okay, and I know that once I have this, I will know that the red color ray, the second ray, if I extend back, okay, it will actually hit the same point here. So what I do is I extend back, okay, I will hit the object. So what I do is I know that the second half of the ray number 2 is actually the same line as your dotted line. So what I do is I just extend back and I will be able to cut the focal point. Remember, draw arrow up, and this intersection here will actually be the focal point for the lens here. Of course, here, why because I do not have a ruler here. So in your paper, remember all the rays have to be in straight line, have to use ruler. Okay, so please go ahead and try on your paper and try to draw this or redraw this image using a ruler accurately. Then after that, what you do, okay, from here, once you get the ray, you can actually label it F. If needed, the question will ask you to measure. So you just measure the focal length if needed. Now, same thing here. The other common question for lenses is this particular question here, 6B. What happens if when bottom half of the lens is blocked, be it top half or bottom half? Okay. One of the common question is, hey, if I have a smaller lens, because why? Because the bottom half is being blocked. So now my lens is actually smaller. So most common thing will be like, if I have a smaller lens, most instinct reaction will be, hey, I most likely will get a smaller image. But sad to say, this is not the case. Okay, so be it bigger or smaller lens, okay, the image form will actually be the same height. That will be at the same locations because the lens is still the same. The focal point, be it half the lens or maybe 3/4 of the lens, the focal point of the lens is still remain the same. Nothing changed. So that's why, even though I have a smaller lens now, I still have the same focal point for the same lens. It's, even though it's smaller size, but the specs is the same. So I will have same focal point. And if I have the same focal point, okay, most likely here, I will mean that the image will actually be the same place. Image will be the same location. So in terms of location, nothing will change. Okay, it doesn't mean, oh, I have half the lens, or maybe my image will actually be half the location. No, it's not. It's still the same location, still as far, still twice, still upright. What actually will change that with the smaller lens? With the smaller lens now, okay, less lights, okay, less rays or less light, okay, enter the lens. And when less light enter the lens, my image form actually will be dimmer, will be less bright in this case. Okay, because the smaller the lens, the image, remember, the image is still the same. Okay, but it's just that because now I have a smaller lens, the amount of sunlight that passing through the lens, will be lesser. And because the number of light ray passes through the lens is smaller now, my image form at the same location, okay, same property, upright or this, the image now will actually be dimmer. Okay, because less light enter the lens. So one of the most common change, one of the most obvious changes we have here is actually the image will actually be dimmer. Okay, so this question I would say is quite a common question that actually keep appearing at like different prelim papers or even O-level paper. Okay, so you may want to take note of these particular changes. For question 7, will be your electrostatic question. Okay, electrostatics involve like positive charge, negative charge, light charge repel, and light charge attracts. So these are the keywords that commonly appear in the electrostatic question. So first one, okay, first one is most common is how does it happen? So when you say how does it happen, they consist of two parts. First is how do I get the gases to be charged first. Remember, the gas, when it passes, enter the chimney at first. Okay, if I don't do anything, the gas won't be charged. It will just be normal gas with all the carbon shoot, all these things inside, but it won't be charged. So the first thing for purification, the first thing is you need to make sure that the dust particles are charged. Okay, and this is what question 4A is about. Is how do I get the dust particle to be negatively charged when they pass through the metal grid? Important thing is to pass through. Okay, now what happens is when the one of the common things is that the electron grid, the metal grid here, okay, in this case, based on the question, is charged negatively. The metal grid actually, when you look at it in real life, you'll find that the metal grid is actually very, very tiny meshes. Okay, it has to be like almost the same size, but okay, as the gas particle, almost not too big, it's almost. Okay, it's almost the same size. So what happens is that the dust particle now will actually go through the grid, squeeze through the grid. Okay, we'll squeeze through the grid. And when they squeeze through the grid because of friction, you'll find that the dust particle, right, dust particle will actually gain electrons from the grids. This is what we know as charging by friction. Right? Because why the dust particle, when it squeeze through the grid here, he will actually rub against the grid, and the grid being negative charge, the dust particle will actually pick up the electrons from the grid itself and become negatively charged. And from there, okay, when they pick up the electrons, the dust particle will now have excess electrons, and because the excess electrons, it will be negatively charged. So this is the first stage, whereby the dust particle actually go out the chimney, it actually squeeze through the grid and it pick up the negative charge from the grid itself. Now, for the second stage is how do I purify it after the charge? Okay, so at this moment in time, the gas that's going up here, okay, they are negatively charged. Okay, the gas that are going up here negatively charged. So what happened to the dust particle? Okay, remember there are two particles inside, the dust particle and the air particle. Okay, remember dust particle is almost the same size as the grid. The air particle is much, much smaller. So the air particle actually can pass through the grids easily without picking up any charge at all. So in this case here, what we have is you have a mixture of dust particle and a mixture of air particle. So my air particle, I would say this is orange color, this is the beige color one, so the green color is the dust particle. So now what happened is the dust particle, which is negatively charged. I remember the dust particle is negatively charged. This guy is negatively charged. Okay. So what happened is it will be attracted to the positive charge plate. So the green color one will be attracted to the positive plate here. So the green color, okay, charged ashes, it will be attracted to the positive plate. Why? Because unlike charge attracts. So these are the keywords that we need to write. And because of that, you'll find that now my dust particle actually go to the left and right to the positive charge now. So what is left behind is actually my smoke particle. So my air particle. So my air particle, which is uncharged now, it will not be affected by the positive charge. So what do you do? The air particle now just carry on, it go up as per normal. And because of this action, whereby the dust particle, okay, the charged dust particle is attracted to the plate on the left and on the right, you'll find that in the middle, you'll find that the air particle or the gas particle will actually be free from all the dust particle, will actually be clean. And as a result, when the gas or when the air actually rise up, exit the chimney, the air particle is actually cleaner than what is when it's entered the chimney. And this is how we actually do purification. Now for question 8. Okay, question 8. The important thing I need to take note is question 8A. When we talk about definition, it will be quite straightforward. Please define current, define charges, define EMF. Then we will just copy and paste the whole definition and plug it in the paper. But nowadays, when we look at definition, it will be no longer that straightforward in the sense that they will not ask you, please define the term current. But what will actually happen here is like the question will say, please define current of 2 ampere. Okay, so you have this particular setting here, 2 ampere. Okay, so what they asking for is not just to define current, but define current of certain magnitudes. Okay, the idea of this is actually like to get students to apply that particular definition to the context they want. In this case, if you look at the definition of current, okay, so if I just look at the definition of current, it will be the flow of charges per unit time. Okay, flow of charges, remember the formula is Q over T. Okay, flow of charges per unit time. But what happened to the let me take a look first. What happened to the 2M? Okay, so where does the 2M come from? The 2M is whereby the student need to phrase the definition with respect to the context. So the context here is 2M. So for my current to be 2M, what inherently must happen is for the current to be 2M, to be classified as 2M, okay, it must have 2 coulomb of charges flowing through the wires or conductors at 1 second. Okay, so this is what I mean by I use the definitions, but with context. In this case, it'll be 2M. So that's why it has to be 2 coulomb, okay, per unit second. So whenever we talk about definition, okay, with reference to context, you must phrase or you must phrase your definitions to make sure that you actually answer the question itself. And in this case, the definitions or to rephrase the definition is to break down the definition of current, okay, into 2 coulombs and 1 second, or what I call per unit time. Okay, so remember, the task for definition is not just breaking down the words to simpler form. It also includes breaking down the number in simpler form. Okay, so that's why for this question here, it's utmost important that student actually mention 2 coulomb of charge. Now for part C, what happens is when I replace it with copper plates at where? R3. Okay, remember copper plate. The idea of copper plate is where? Copper plate is of low resistance, and in this case, it's like almost negligible. It's one of the best wire that we have with negligible resistance. So what happened now is I actually replace R3 with a wire here. So this is the copper wire. Okay, so with this copper wire here, in fact, actually, this path actually now become what we know as your short circuit path. It become a piece of wire. So because of zero resistance. So this path actually has zero resistance. So same as before, now when my current passes through R1, it will still be active. So with the moment I come to this node here, this particular junction here, previously without copper plate, with R3, current will still go down to R2, current will still go to R3. But now with copper plates, none of the current will actually go down to R2. Why? Because now my path is actually 0 ohms. 0 ohm, all the current will actually take the path of 0 ohm. Oh, yeah. Because the resistance on the other path is 0 ohm. Okay, it's not just small, it's the smallest of all, it's 0 ohm. So in fact, this path will be rendered short-circuited, it will be rendered useless. And no current will actually go through R2 because all the current will actually go through R3, which makes this circuit now a series circuit, which consists of R1 only. Okay, so this is what we mean by taking note of what the question asking. And in this question here, the keyword here is the use of the word copper plate. Okay, so it will cause the path to be a perfect wire, and what happened is you will divert all the current from A2 from R2, okay, and no current will flow through A2. Okay, so A2 will be shorted. Okay, so students, you need to take note what are the possible changes when we look at. Okay, in this case here, I would say the important things the students have to take note is the use of the word copper wire, a copper plate or copper wire. Know what does copper plate means, and from there you will deduce the possible effects. Okay, so question 9. Question 9 involves Fleming left-hand rule. Now, first thing first, the questions this particular question is actually quite interesting because he gives you the motion first. Most of the time in Fleming left-hand rule, the standard question would be the question give you a battery, they give you wires. With the battery means I know the current, and the last thing I give you is I give you a magnetic field line. Why? Because I'm asking for the induced forces. But in this case, the question actually reverse it. The question actually gives you the direction whereby the rod will move. In this case, it will be moving to the left towards AC. So what happens is that he actually asks for the battery. Okay, so here, what we are looking at, remember, but we still need to apply Fleming left-hand rule. So we have to apply left-hand rule. Fleming left-hand rule, take notes. Okay, the index finger represents the field lines. In this case, X. So it means your index finger actually move inwards to the paper. And based on the question, you know that the rods actually go towards the left-hand side, which means your thumb will actually point to the left. And when your index finger point into the paper, your thumb point to the left, it will bring you to the fact that the current will actually be pointing upwards. So which means for the rod to be going left-hand side, my current must be in this direction upwards. Okay, so my current has to be upwards. In this case, means if you trace the wire here, it will be coming down from Y, go up the rods and go down an X, or what we call the current flow should actually be clockwise direction. And with clockwise direction, okay, it will mean that the battery will have to be in this terminal. The battery will be in this arrangement whereby this is the positive side, this will be a negative side. Remember, current flow from the positive terminal to the negative terminal. So from here, I'll be able to deduce that the battery is actually placed in this orientation. And as usual, Okay, what is the component that is missing at position D? Remember, I will actually need a rheostat. Okay, from here, one thing to take note is the students, sometimes the question will ask, why do I need a rheostat? Okay, as before, remember the use of the rheostat, okay, the use of the rheostat, or what we call your variable resistor, okay, is why? As I want to restrict the current for the safety of the appliances. Why? Because at the beginning, my rheostat has to be set at maximum resistance. Why? When I set at maximum resistance, I will have minimum current flowing through the circuit. One purpose of this is actually to restrict the current. So I have minimum current. Let me write it down properly. So I have minimum current in the circuit. And what does this do? It will actually prevent, or it will actually reduce the heat generated, and it will actually protect the circuit from overheating. Okay, now for part B, state the effect of increasing the current, increasing the current, right? Increasing current on the motion of the rod. This, I would say, this is quite straightforward with a greater current. Okay, but the keyword here, most of the time we say people will know it's like greater current, greater force induced, and from there actually move the rod faster. And the rod will move actually faster. So remember, your answer need to end off with the motion. Don't just tell me how larger induced force, where you must tell me the motion, which means the object will actually be moving faster, or the speed will be increasing, or there will be a greater acceleration. So look at your question, answer precisely and concisely. With higher induced current, with higher current, yes, by Fleming left hand rule, the force induced will be higher. This is the standard answer that we look. This is by Fleming left rule. But the question looking at the motion. So you have to end off with, you have to continue to tell me about the motion, whereby you talk about the speed, you tell me the acceleration, or you tell me the motion. Okay, so look at the questions and craft your answer accordingly. Okay, most of the time I agree that the question will actually say, oh, give me identify certain ways, or identify the effect of increasing magnetic field line on the induced force. So you stop at induced force, but not all questions will be asked that way. So students, you have to read the question carefully and phrase your answer precisely. Question 10 is a aquarium air pump for solenoid. Okay, there's a solenoid here. Whenever I have a solenoid here, one of the things I caution myself is actually, please go and look at how the coil is actually being, how the solenoid is being coiled. Because by identifying how the way it's coiled, I'll be able to identify the North Pole and South Pole induced by using Maxwell rule. For example, you take a look, okay? For this case, remember the coil is outside here, go in. So which means if this is the current will actually be flowing upward first, go down behind the magnet, and come out from the bottom of the magnet here. So between the current will be going upwards this way. Okay, so if you use your Maxwell rule, okay, you use the Maxwell right hand rule, you grip the thing. So in this case, the wire is actually the current is actually moving from bottom up. So if I grip it this way, my finger will be the current, my fingertip will be the current. I grip it upwards, I let go my thumb, you will find that my thumb actually points to the left. So my force induced, my magnetic pole induced is on the left, my south pole induced will be on the right. Now in this case, let's take a look. Okay, explain how does the lever system vibrates when the switch is closed, or basically explain how does the device work. Now for explanation question, usually the question I will always tell students, sometimes I really don't know, or you really don't know how it works, but the question has clue or has some important checkpoint for you to run through. So one of the checkpoint that we're looking at is actually the labeled parts. So always look at the labeled part. The labeled part will actually tell you where does the whole thing starts. In this case, the labeled parts, there are quite a few labeled parts that you need to take note. So all these are like electrical source, North Pole here. Okay, you have a rubber pad, you have air outlet, okay, outlet, and you have valve here. Okay, and of course the word electromagnetic. So these are the clues to tell me how, when I describe, I need to use these words. Where do I start? From this question here, you will know that the aquarium pump, the right side, this is the final stage. Okay, and if right side is outcome, I will know that this will be maybe the starting point. So in fact, okay, I will know that my source is my starting point. Which side do I start? I'll look at the system. In this case, we know that the output is an air pump. So between the right side will actually be I would say the final stage lah. So between the inertial state will be where the electrical source is. And usually source implies starting. I would say it's starting lah. So what happens is when the current actually is connected. So I'll start from the electrical here, source here. So and true enough, this is where I start. Okay, so when I switch on, the electromagnet will be magnetized. Okay, and how do I know I need to write my electromagnet? Because the question's labeled this way. So I only bring in the electromagnet. Okay, then after that, what happened is I will need to take note of where is the M. Okay, it will be attracted, okay, to the electromagnet. In this case, I know it's alternating pole. Okay, so the pole will be alternating. So in this case here, because it is alternating, so this south pole induced and this north pole induced will be actually swapping places. Because the alternating current, the current will change between my north pole and south pole will change place very fast within a few 60 times, 50 times per second. So now what happened is my electromagnet is energized, is magnetized already. So my magnetic M will be attracted. Okay, my magnetic M will be attracted because this north pole will be attracted. Okay, and remember the question talk about alternating source. So which means sometimes this is south pole here. If it's south pole means it will be attracted. But on the other hand, if it's north induced, south induced. So now what happens if it's north induced, north and north, the pole will repel. So that's why I have a series of attraction and repulsion, which is this, make these two the keyword here. Remember, how do I know it is attracted? Because based on alternating source, it's possible that my electromagnet will be south pole at the bottom. How do I know it will be repelled? Because alternating source again, I will know that the south pole, south induced pole at the bottom will actually change to north induced pole later. So that's why I will, the bottom side of the electromagnet, it will actually alternate between north pole, south pole, north pole, south pole, north pole, south pole. And as a result, I will have a series of attraction and repulsion. Okay, so which means the north pole here will be actually be going attracted, then you'll be repelled left and right, left and right, left and right. Okay, so when it's left and right, what happened here is I actually have a pivot here. Okay, so this guy will be, this pole here or this bar here will be actually moving left and right, left and right, left and right. Okay, so whenever the north pole move left, the whole thing will shift together. And when this bar move left and right, the rubber pad will be squeezed, compress, release, compress, release, and compress, release. And as a result, okay, the lever system will literally vibrate. In this case, it will be moving left and right. And this left and right movement actually help me to pump air. And that's where your air outlet come in. How do I get this thing to pump out? It's because my lever actually vibrates or move left and right. And this motion of left and right compresses the rubber pad. And when the rubber pad is compressed, air is being pushed out of the air outlets. That is how the whole system works. I would say the system is more complex than it seems. But true enough is that with the labelings and with the inference, students who should be able to infer how the whole system works, okay, accordingly, based on what is given to us. So I would say that the marker is actually quite kind enough to actually give us, to label all the things clearly so that it serves as a guide to the student. So that's why whenever I tell students to describe how an appliances works, it's important to actually analyze the picture first. Look at what are the labeled items that is given, and from there, look at the questions to see where should you start. The question will actually give clues to students to tell the student, hey, you actually should look at this area first and start from this area. Common thing will be, say, sometimes the question will give you arrows. You draw arrows to tell you this is the starting point. Sometimes the question will give maybe some labeling, say input or maybe power source, all these things which symbolize that could be the starting point of the whole system. What will happen to the lever system if when the AC source is replaced by a dry cell? Dry cell here is DC, yeah? Okay, so which means the north induced pole here, the north induced pole here, okay, north and south induced pole will no longer be alternating. It will no longer be changing. Because why? Once I replace it with dry cell, yes, my electromagnet will still be magnetized, but now the current direction never change. So usually my electromagnet will actually be magnetized with a particular pole only. It could be, example, south pole only. So which means that the pole, once I only got south pole, I will actually permanently attract M. And when I permanently attract M and I don't repel it, my M will not move left and right. My lever will no longer vibrate. And when my lever don't vibrate, air won't be pumped out of the system. And same thing here is now section B, question 11. Question 11 deal with some forces, friction. I would say more dynamics and kinematics. Okay, now remember based on the question, I have 12 kg. I have two surfaces. Okay, A, B, and B, C. By this, A, B is here, A, B is here, this surface. Then I have B, C. which is this surface here, this rough surface here. Okay, and this graph that we're looking at is speed time graph. Okay, so the more I have speed time graph, I need to take note is that it could be like the area under the graph will give me distance traveled. The gradient of the graph will give me acceleration experienced by the object. This is one of the main keyword concept of your kinematics. Now, the block experience uniform acceleration from A to B. Uniform acceleration, define uniform acceleration. This one I would say quite straightforward. Okay, so you define what the textbook say lah. Okay, then after that you have the calculate the acceleration. Okay, so this one quite easy. There will be the gradient of. I would say that's why it's important to look at the graph, because the acceleration will be the gradient of AB, of the line AB. Okay, so same thing. This is the main concept of gradient of AB. Okay, so these two I will not dwell too much because these are quite straightforward questions. Now, force applied, same thing. I would say it's the Newton's law. F net equal ma. Okay, part B will give you the acceleration. Okay, and mass is actually 12 kg. And with this, I should be able to find the net force even. Okay, easily done. 1 mark. Okay, now explain in terms of forces why the speed remain constant at BC. BC, there's a frictional force. BC, there's frictional force. Okay, and this frictional force, what actually happens? Okay, now let me draw the object here. So in this case, I have applied force. I have applied force here. And based on the question, because it's the rough surface here, I will actually have a friction here. Okay, so in this case, here there's a friction. So if you look at this question here, I'm looking at the net force, which is F net equal to ma. In this case, it will be big F minus small f equal to ma. Okay, so in this case, there's a friction along the surface. Now, what happens is when is the speed to remain constant. Okay, speed to remain constant. Constant speed, one of the important thing is actually acceleration equal to 0. So when acceleration equal to 0, it will imply that, so within my right hand side will be 0. And this will allow me to deduce that the force and the applied force is actually the same. So this will tell us big F and small f, they are actually the same values. And from there, I'll know how the force, the sizes of the force here. And from here, I'll be able to deduce, okay, why the object actually move at constant speed. Okay, so this is what we mean. Or there's a name for it, a phrase what you call terminal velocity. The rest, I would say the total distance traveled by AC. This one, like I mentioned before, this is what we mean by distance. AC is a kinematics. A to C, it will mean the area under the graph. Remember, speed time graph, area under the graph will give you distance. So this area here will actually be the distance traveled. So in this sense, distance traveled by AB is actually the triangle. BC, the distance traveled is the rectangle. Okay, so by finding the shapes of A and B, these two shapes, I will be able to identify the total distance traveled by AC. Quite easily done, actually. Calculate the kinetic energy at C. This one is easy also. Why? Because kinetic energy, we all know the formula is half mv squared. And I know this speed has to be the speed at C. And what's the speed at C? And the good thing is speed at C is constant speed. And how do I know? Because the question says speed is actually 20 meters per second. So this is actually VC. So I know the speed is actually 20 meters per second. And from there, if I substitute a number, I should be able to get the energy in the kinetic store, which is what your calculator says. So I would say it's straightforward. That's why it's only worth 1 mark. The applied force is removed at C. Okay, and it decelerate and eventually come to a stop. Okay, so which means if you look at the decelerate, and previously I have kinetic energy, so the applied force is removed at C, which means that the friction still exists. And this friction is the one that actually caused the object to decelerate and eventually come to a stop. Which means that the energy I have at the beginning, which is actually energy at the kinetic stop, and the energy I have at the end of the day is actually given out, okay, transferred where mechanically by work done. The work done by who? By the friction. So if the work done by friction, okay, which is what I mean by this equation here. Work done by friction, it will be force of the friction times D. Okay, so in this case, what is the force that we are looking at? Okay, what's the force we are looking at? Which is 80 Newton. Okay, so once I know the force is 80 and I know the energy, which is from part F, then from there, I will be able to calculate the distance traveled, which will be 30 meters. Okay, from here, yeah, okay, the stopping distance needed is actually 30 meters. Now, so now is the choice between question 12 and question 13. Now, question 12, okay, Nicholas set up the experiment here. There are some boiling involved. There are some boiling point here. So you'll be most likely deal with kinetic theory, okay, kinetic particle theory, all these things. Okay, so let's take a look. Water has a boiling point of 100 degrees Celsius. Define a boiling point. Yep, no, nothing too difficult. Okay, standard definition. Okay, so okay, just look for your book and look at the boiling point, definition of boiling point, which involve okay the particles changing states at a certain changing state, what state, liquid to gas, okay, at a fixed temperature. Now, kinetic theory, using the theory of matter, explain why the temperature of water remain constant when it go boiling. Now, for this question here, this is a standard, I would say it's a standard explanation, but there are things to take note is that during this explanation, although we are referring to kinetic energy, we are referring to temperature remain constant, which means the students will know that temperature is related to kinetic energy. So basically, if the question, some student will argue, say, hey, since the question asks for temperature, should I just explain EK only? And the answer is no. Because when the energy is input to the system, the energy, the whole processes actually is one set. It involves energy given to either EK or EP. So by explaining either one of them, even though you are being concise, but you will render the explanations fairly incomplete and I would say it's error. Okay, so that's why when we look at this explanation for boiling, for melting, for heating, it's important to actually mention, okay, two segments, the EK and the EP. But together, okay, these two will actually describe what actually happens to the water when it's boiling or what happened to the water when it's heating up. These two explanations, the explanation for EK and EP, okay, together, these will be the complete explanation. EK and EP is like half the explanation, but half the explanation, giving half the explanation, although I answer the question, but half is incomplete. And incomplete, you will render the whole explanation incomplete and useless. So that's why to have a whole picture of what happens during the heating process, to what happened to the particles, we need to touch base on what happens to the EK, okay, and what happened to the EP. Okay, so you have to take note of this. So, and when we talk about EK, the most straightforward one, we look at the speed. Okay, we look at speed, we look at the constant. Then after that, we deduce temperature is constant. That's quite straightforward. But what happens is when you look at EP, there are certain categories. EP, we look at two segments here. Their energy is given. It's definitely work done. And the most obvious one when you look from liquid to gas phases is whereby the bonds are being broken, bonds are being weakened further. So which means that there's work done against the intermolecular bonds, okay, to weaken the bonds, okay, for the object to actually increase the separation. Because why? Because in order for the gas to actually change from liquid to gas, this atomic distance has to increase. And to increase, one of the criteria I need to have is I need to weaken the bond first. So that's why one of the energy, a portion of it is given to the work done to break the bonds. But this is not the only one. The other portion will actually be used to push back the atmospheric pressure. Because for the gas to escape, to move far apart, to move far away from each other, two things must happen. They must have a weak intermolecular bonds, which we accounted. You already settled already. Second one, the gas must be able to overcome the atmospheric pressure and move out of that confinement. Two areas where energy are being used in this case. First, to actually work down against the intermolecular bonds, and actually second one, to push back atmosphere. When these two are achieved, your molecules are able to break free, okay, and are able to roam the atmosphere freely, and what we call the gas particles are able to move around freely, or what we call your not confined to fixed position, all these things. So for this to achieve, I need to settle and give energy to number one and number two. Okay, so when you talk about EP, these are the few things that you must settle. When you talk about EK, you must talk about velocity, you must talk about temperature. So different energy, they got their own respective keywords and their respective users. So students, you need to know at each stage, at what stage, at melting, at boiling, at heating, okay, you need to know what energy, where does the energy go to? Is it going to EK or is it going to EP? Now, part B is talking about transfer of heat, thermal processes, conduction, convection, radiation. So in this case, I will not dwell too much because I would say this question is fairly straightforward. Now, for part C, okay, part C calculation. Calculation, you are given a heater which is 500 watts. Okay, you are given 500 watts and 240. Now, to calculate the fuse, whether it's applicable or not. Okay, to calculate the fuse, I need to know whether the current, the size of the current first. And first thing I need to do is I need to find the current size using the formula P equal to IV. And from there, I will know that the current will be 2.08. Okay, 2.08 is definitely bigger than 2 amp fuse. So if I use a 2 amp fuse now, I will definitely have, my fuse will definitely break, and I will definitely disconnect the whole appliances. So that's why I would say my 2 amp fuse is actually not applicable. Okay, students, you might want to take note is like, please go and remember, take note of what are the appropriate fuse rating that is in the book, that's given in the book. Okay, so please know the rating. Yeah, I also leave the rating below so that you know what are the fuse rating that are suitable. Remember, one of the cue for choosing the right fuse is you need to choose a fuse that is slightly higher than the current one. Okay, so just take note of this. Now, for energy calculation, okay, I would say for cost of calculation, cost of using electricity. First thing first, if I need to find cost, I need to find energy first. Okay, to find energy of electricity in circuit, the formula I have is PT, which is here. Now, whenever I deal with cost of using electricity, I always remind myself, I need to find energy first. Because why? Because costing, the standard, when they give you the rate, they always give you 40 cent per unit. And this particular unit is where? Kilowatt hour. Okay, this particular energy is measured in terms of kilowatt hour. So when I calculate energy, if I want to calculate cost, okay, I have to make sure my energy is in the unit kilowatt hour. Okay, so it has to be kilowatt hour. And for the energy to be in kilowatt hour, I must have certain condition. My power must be in kilowatts. My time has to be in hour. This is the only formula for the science physics, right? This is the only formula that doesn't need SI units. Of course, energy, if you look at the proper definition, if you look at the calculations, energy, if I want the unit to be in joules, if my energy is in joules, I will definitely need my power to be SI unit watts, my time to be SI unit second. Yes. But in this case, for calculation of electricity, the energy unit given is actually kilowatt hour. So the energy for calculating electricity is actually kilowatt hour. That's why it's 0.5 kilowatts. And time here I use actually 5 hours. I don't need to change to second. Okay, once you got the energy, which is measured in kilowatt hour, you just multiply by the rate, and you will know you will have the total cost for using this particular electricity. Okay, so for calculation of costing, energy use or calculation of the use of electricity, remember you need to find energy at first, and the energy has to be measured in kilowatt hour, which will bring us to the fact that power has to be in kilowatt, time has to be in hour. Question 13, okay, filament lamp. Okay, question 13, okay, two resistance, okay, of A and B. Now, talking about resistance, okay, current voltage graph, okay, it's important to take note, okay, when we talk about gradient for graph, okay, for IV graph, to calculate resistance from IV graph, the resistance is not the gradient of the graph, it's the ratio. Okay, so for resistance, okay, to find resistance from IV graph or VI graph, it's important to find the ratio of the graph of I and B. It is not the gradient. There's a subtle difference between them. You won't see this difference if the graph is given like what YA and YB. It all starts from the origin. Yeah, but what happens is VI graph, that don't start from origin. Okay, so what happens is if I don't start from origin, the gradient of this graph will not give you the resistance. Okay, so point to take note is that for IV graph, to calculate the resistance, you have to use the ratio of the IV, not the gradient. Okay, it's not important that students, you know the difference between gradient and the ratio of the IV graph when calculating resistance. Okay, because this particular question actually come up before in MCQ and in structure question. Now for this question here, yes, okay, because of the graph given, the resistance of the graph, okay, it will be the ratio of okay, of VI. Resistance is V over I. So for this particular question here, we are looking at, okay, for wire A, the V is 3 volts. Oh dear. Okay, the V is 3 volts. Okay, and the current for A is 0.6. So this will be 3 volts and this will be 0.6 amp. And the answer will appear. Okay. Okay, now the resistance, okay, wire A is connected to the EMF 24 volts. Define EMF of 24 volts. So remember, so you look at this definition, you need to break down the word EMF and you need to break down the word 24 volts. And definition of EMF, it fall back on the formula that potential difference or EMF is the energy per unit charge. Okay, so you break down the word EMF, it will be the work done of the source to drive a unit charge around the complete circuit. If you break down 24 volts, it will be 24 joules per unit charge. Okay, so that's where the 24 joules and the unit charge come arise. Okay, so remember when we look at definition that involve context. Okay, remember to break down the definition in terms of the factor itself and the value itself. Okay, so just take note of this. So the 1 mark of in terms of definition, it doesn't just involve giving the correct definition. It involves correct definition plus the correct context. Okay, so once you have that, okay, I will say the formula EMF, the formula I mentioned before, is work done divided by charge. Okay, charge is Q. Okay, EMF is given a question. It was straightforward question, so I will not dwell too much on this. Part B is dealt with critical angle and total internal reflection. For students taking the new syllabus now, okay, the new syllabus for you guys do not have critical angle and total internal reflection. So that's why I skip this particular question for you. Okay, so just take note of it. There's a subtle difference between the old syllabus and the new syllabus. Okay, one of them is your total internal reflection and critical angles. Now, a small pebbles is dropped in the water in this case, and this you have the displacement distance graph given here. Okay, displacement distance. Okay, now water waves. Okay, remember most of the time, how do you identify longitudinal and transverse wave? The most easy one is that just remember, okay, for longitudinal wave, the most obvious, you only got one only. Most obvious is sound. Sound is the only longitudinal that we have that we cover in the whole syllabus. So, and most of the time, 99% of the wave that is given is actually transverse wave. Okay, so basically, once you identify transverse wave, then you can actually explain it using definition of transverse wave. Now, speed of the waves, if my frequency is 15 Hertz, so speed of the wave is wave formula V equal F lambda. I want to calculate speed, I have the frequency. Well, I need the wavelength. So where do I find the wavelength? Definitely from the picture here. So displacement distance here will refer to the wavelength here. Okay, so the one cycle for this would be the wavelength. So from the graph, you'll know that the one cycle here will be actually 12 cm. So you know this is 12 cm. Frequency is 15 Hertz. You multiply them together, the product will give you the speed in terms of cm per second. But take note, the question asks for meter per second. Meter per second, which means this 12 cm, you must change to 0.12 meter. Okay, so this is what we mean by common booby traps. Okay, so these traps are actually quite obvious. Okay, so you must avoid them. Okay, conversion to SI unit, all these things depends on the question itself. If the question actually speed doesn't need to be meter per second, no need. You can leave it in cm per second, no problem. But it's just that for this case, the question insists that you actually want it to be meter per second. So that's why you have to follow through and actually convert your distance to become your 0.12 meter. Okay, with this, we will come to the end of this particular paper here already. Okay, now we have come to the end of the video. I hope the video has been useful for you. Now, the subsequent week, I will be uploading videos on certain chapters or on certain concepts that my students are asking. So if you want to get notification of these videos, okay, remember to subscribe to my channel and remember to press or to activate the bell button so that you will get notified the moment I uploaded the video. And I hope the video that I uploaded to you will be useful for you also. Okay, now, without delaying, okay, this is where I end off. Okay, I hope to see you soon. Bye-bye.